I am Tommaso Julitta from Hyperspectral Devices, and today I prepared a presentation which is a bit more narrow compared to the broad and great overview that Juan was giving during the morning. So I will talk about how to measure sun-induced chlorophyll fluorescence in the field, and also reflectance and vegetation indices and so on. And this during the first half-hour open lecture, and then I was asked also to present sort of a live demonstration how the data processing can work, how to handle the data we can get from our devices. So I structured the presentation this way, so a brief introduction of the company, then a bit of theory, a focus on how the instruments are working, and then finally a case study making use of the data collected with the FLoX, which was installed for 3 years now in Svalbard. So just to do not go too far from the topic of also the Arctic community here. The company, so JB Hyperspectral Devices is a company, a German company founded in 2016, so it's now already 5 years we have this company, and our main focus is the design and production of advanced hyperspectral field instruments. So basically we are integrating spectrometers, usually used in the lab, into field devices, which means that they can operate in a longer term perspective in the field, and monitoring most of the target the researchers could be interested in. In particular, we started up the company making this FLoX instrument, which stands for fluorescence box. So we are really devoted to the accurate measurement of sun-induced chlorophyll fluorescence, and to make this parameter available for researchers for their purposes. But since the sun-induced chlorophyll fluorescence is a really tricky signal to measure, we got some experience, and then we could amplify, let's say, our offer, and we are now making also other kind of instrument which can be used to monitor other environmental variables, for example, water quality, snow optical properties, and yeah, plant physiology as well, or plant phenotyping. Yeah, I mean, now we're broadening quite a lot in terms of application. A bit of theory. I think that most of the theory was already gave by Juan this morning, but I wanted to give you more specific details on how, for example, to get the estimate of fluorescence with the spectrometer in the field. So going back to the question, what is fluorescence? Fluorescence is basically energy emitted by light emitted by plants at a lower energy, which means at a higher wavelength. And if we look at the plant, we can see usually the green color because of the chlorophyll content. But if we are able to excite this plant with, for example, a blue light in a dark environment, and we have some filter in front of the camera, what we can see is this red glow, which is exactly the signal we call fluorescence, because this fluorescence is taking the excitation at a lower wavelength and is emitted in the red and near infrared. So this is something we can only see if we have some filtering technique, because this signal is really tiny. So in the field we cannot really see this red glow, but we can see it if we can use some particular technique to detect it. As Juan was already saying, this fluorescence signal is emitted during the photosynthetic process. Actually, is one of the 3 main pathways the plant use the light. So there is the photochemistry, so photosynthesis, then heat dissipation, non-photochemical quenching, and a smaller part of that is also emitted as a fluorescence. So basically, knowing and getting this information could really help in describing better this photosynthetic process. which is the aim of all the researchers which are now really taking off in the last years, especially on sun-induced chlorophyll fluorescence, because is expected to be a really important parameter which could improve the estimates of photosynthesis in general, which can have a lot of application as well. The tricky thing is that this is not solving all the issue, because knowing or being able to measure fluorescence doesn't mean that we are able to directly infer the photosynthetic rate or photosynthesis of a plant, of a leaf, because it's not always directly related. Actually, there are few circumstances where this direct relationship is valid, whilst if the plant is exposed to other environmental stress, for example heat, then the relationship invert and become an indirect relation. So it's really complex study, and this is why still is let's say on his is a like a hot research topic at the moment. And how to measure it in the field. So in general, if we are talking on sensing technique, we can divide it into active techniques or passive techniques. Active means that we are making use of artificial light to excite the plant, and then we have a detector which record what is emitted by the plant itself. This is, let's say, the active measurement techniques, which can also be applied for fluorescence. There are a few instruments to do that. One is the leaf sensor reported here, but also it can be measured passively. And here the tricky part is that we need to disentangle the emission of fluorescence from the radiance reflected by the plant, which under normal sunlight condition is really minimal, the fluorescence. We are talking about 2%, 5%. And this is the estimate of the solar-induced chlorophyll fluorescence. And what makes really tricky the retrieval of fluorescence using this passive method is the fact that the fluorescence is really low compared to the reflected light or to the environmental light in general. So in the last decades, several retrieval methods, several techniques to disentangle these two radiances, fluxes, were developed. And most of them are based on the use of atmospheric dark region. If you can see on this plot, I highlighted these two bands, which are called oxygen B and oxygen A band, and these are the absorption feature in the solar radiance that you can measure at the ground due to the concentration of oxygen. In this region, basically, a very few amount of light is reaching the surface, and luckily these are overlapping pretty well with the emission of fluorescence, which occur in between 650 nanometer and 800 nanometer. So basically, by exploiting the information that we can get inside this oxygen band, we can get the estimate of sun-induced chlorophyll fluorescence, which is not a direct measurement, but is an estimate, so it's a retrieval. Therefore, this also depends, to get accurate measurement of fluorescence, it also depends, apart of the accuracy of the instrument, but also on the accuracy of the retrieval method you are applying to. In this graph, I reported the graph from Meroni in a paper published in 2010, where basically we can see the apparent reflectance, which is a normal reflectance of the vegetation, and you can see that at 760 nanometer, which is where the oxygen A band is, and also at 687, you can see a peak, which is basically due to the infilling of the fluorescence when we are calculating the reflectance as a ratio between the reflected radiance and the sunny radiance. So this peak is basically due to the contribution of fluorescence. The same, but not as evident in the other oxygen B band, so at 687 nanometer. And this is basically what we want to measure. So you can see that is minimal. And there are many techniques which really rely on this small and tiny peak determination in the apparent reflectance. In this slide, I was just reporting a sort of brief history of the top of canopy SIF retrieval methods, which were developed since the 70s. And then you can see a big lack in terms of years. And then when mostly the spectrometers became available at a cheaper price, many researchers tried to use them and develop new methodology. Each method which was developed, since we are talking on a retrieval, on an estimate, has some assumption and some limitation, and this is why it's a continuous story. Try to reduce the error in the estimate and improve the accuracy. I put as a headline like this is a FLoX mission, which will be the first satellite explorer mission completely devoted to the retrieval of fluorescence, which will occur not in 22, but probably in 2024. And some of the methods I'm also presenting there are close to the one implemented in the satellite estimates. Here I focus on the method. This is called Fraunhofer line depth, which is basically this method is basically comparing the depth of this absorption feature from the atmosphere with the one coming from the reflected, so from the target itself, and is by simplifying a bit the method, making the difference between the two, we can find the difference, which is the fluorescence signal, so the infilling on this band. In this case, there are some assumption, which means that the fluorescence in this range is stable, is constant, and this is not the case. So other methods were published afterwards, improving the assumption of the shape of the reflectance and the fluorescence in this domain, which were improving the accuracy. And finally, let's say the approved method also for the FLoX mission from the European Space Agency is based on these spectral fitted methods, which is a sort of statistical approach to disentangle the two components by applying a spectral fitting in this range, and can give us as an output the fluorescence and the real reflectance, so the true reflectance. This is pretty good because most of the method before could only give the values at two specific bands. In this case, there is also a reconstruction of the spectrum, which of course is making the retrieval more complex and prone to other issue in the retrieval itself, in the statistical approach. And this is, for example, the output you can get with real data that you can extract the full spectrum by minimizing these cost functions, so the modeled and the real measurement. I was saying that FLoX will be the first mission, satellite mission, to measure fluorescence from space. But other mission with sensor with characteristic which could be used for, which can be used for retrieving fluorescence, were already in orbit and already used for retrieving fluorescence. For example, there is a paper from Luis Guanter in 2014, which was showing already the potential of using some of them to retrieve fluorescence and correlate that with, for example, in this case, drought event in the US. But yeah, the next one will be FLoX, which we hope will be able to give more insight into this and provide more useful tool for the researchers. I'm making this focus on FLoX because we are collaborating a lot with the European Space Agency, and in particular, our instrument are somehow used as a reference for future probably Calval activities of the satellite, and so we developed them according to the specification in terms of spectral characteristic of the spectrometer of the satellite mission fluorescence FLoX. In particular, going to the instrument, so we are making these mainly these two instruments, which one is the ROX, stands for reflectance box, and is an instrument which is made for continuous and long-term measurement of solar irradiance, reflected radiance, and does reflectance. It has a pretty broad spectral range from the visible and near infrared, from 400 to 1000 nanometer. And it's extremely small size and very low power consumption. The big brother of the ROX is the FLoX, which is containing two spectrometers. One is the same visible near infrared, so the full range, let's call it, as the ROX, plus another higher performing spectrometer, which is devoted to the measurement of sun-induced chlorophyll fluorescence. Because in order to really detect this fluorescence, we really need a super high spectral resolution, a super good signal-to-noise ratio. So the FLoX contain both, one for fluorescence and one for the traditional VIs and reflectance. And here you can see some of the picture of the user, which, like, you know, researchers really have a lot of creativity, so they really find many ways to use this instrument for their studies. And this to let you know that, as I was saying, we were collaborating a lot, and we are still collaborating a lot with the European Space Agency. So these products are a sort of results of several years of collaboration of our also former research group at the University of Milano Bicocca, Jülich Research Center, and also Max Planck Institute in Jena. So during this preparation phase of the satellite, there was happening a lot of field study to demonstrate the reliability of making such a measurement, the importance of using fluorescence for different purposes. And this could support the development of many prototypes, and FLoX in particular, but also ROX, are somehow the results of this long collaboration. And actually, yeah, since 2016, we founded the company, and this is more or less a sort of updated map of the distribution of our devices, FLoXes and ROXes. Some of them are installed permanently, usually close to or in at the covariant sites, so for measuring GPP. But other are just used for other purposes, like specific phenotyping experiment or similar. And actually, going back to one of the questions of the morning, if SIF was used to monitor also lower level plants, I think now things are moving in this direction, because at least I think 3 of our FLoX are trying to go into this direction and monitor lichens, mosses, or biocrust, mostly from arid ecosystem. And one of them, which I will show the data from, is in the Svalbard, installed in Spitsbergen 3 years ago, and still running nicely. These are the characteristics, which you can also find on our webpage. But as I was saying, the FLoX contains 2 spectrometers. Here are the spectral range, interval, and resolution. And as you can see, these are pretty high-performing characteristics if you're not too much familiar with. But in any case, for example, the signal-to-noise ratio is really high in this spectrometer devoted to fluorescence. The instrument, this is an important, let's say, point, as 4 fibers coming out, 2 looking up and 2 looking down. The one looking up are equipped with a cosine receptor, which basically is to make a field of view of 180 degrees, so collecting the full hemisphere of light during the course of the day. Whilst the other one looking down is a bare fiber optic with a 25 degree of field of view. So you can imagine like a cone going out from the downward looking channel and measuring the target you have below, which can be vegetation, for instance. And according to the distance from the top of the canopy, you will have a different footprint of the area. So consider that if the instrument is installed, for example, at 3 meter high, you will have 1.5 meter of diameter of a circle, because we are talking about a point spectrometer, which then has just, if you consider, it could be compared to 1 pixel of 1 hyperspectral images, as the one that Juan was showing this morning. The instrument itself was developed to work continuously in the field, so it is making automatic measurement in a way that is adapting automatically to the varying illumination condition. So if it's really dark, basically it automatically adjusts the integration time, which is a sort of exposure time in the digital camera. So basically, if it's dark, the measurement will take longer. Otherwise, if it's super sunny during the sun, probably the measurement is taking just a few, less than 1 second. So in principle, the measurement interval is 1 minute or even less according to the light condition. Then it contains a lot of other sensor inside to check the temperature stability, the humidity, and so on. Also contains some other metadata information like the GPS position and time. And all the data are stored in these in an SD card, which can then be downloaded, and the data processing can start. We made it for outdoor use, and usually the sites where these instruments are installed are rather remote, so the power supply, we keep it extremely low, which means that it can run with the solar panel. And actually, this is the case for the FLoX installed in the Svalbard. Yeah, and then basically it only runs during the day, since during night everything is dark and there is no real meaning for measuring it, unless in Svalbard, where the summer nights are extremely short. And for the data processing, basically we implement an open source data processing GUI, which is usually made available. Is made available to the customer in order to process the data, and it's open source based on R, so everyone can also have a look to the code. And what this data processing GUI is making, and this is something we also will see more into the detail the next session, is basically converting the raw data, so the data measured by the instrument, into physically meaningful signals or radiance. Then making use of the radiance, calculate the reflectance. And this is, for example, the diurnal cycle of reflectance. Then applying on the radiance and reflectance the retrieval of fluorescence, and all the calculation, the vegetation indices that can be calculated in this spectral domain. And finally, also provide a sort of filtering of the time series in order to account for some quality flag, which again we'll see more in detail later on. And then I would like to conclude with a very brief case study. But as I was saying, this is one FLoX installed in Spitsbergen in 2019, and by Hans Tommervik, who later on will also have a lecture. And in this case, the instrument is installed only during summer, because during winter everything is covered by snow, and is running till today. It collects data from early morning to late evening, and in this case, the target is grassland. As you can see, there is this tripod with the FLoX, so the instrument at the bottom, and on the boom, the fibers looking down and up are installed. I was selecting from the full data set of 3 years of data some of the clear sky day, and this is one of that. It's not that common in Svalbard, but here you can see clearly, for example, the diurnal cycle of the incoming radiance. This is the yellow one, the reflected radiance daily course in light green, and finally the reflectance, which is the ratio of the two, in dark green on the right. You can see that some of in the near infrared, so you can see this wing going up on the right side. This is mostly due to some light effect, so what we call bidirectional reflection factor, which means that the natural environment does not have a Lambertian surface, so the surface is not reflecting equally in all the direction the radiance, and in particular for some low sun angle, this is more pronounced. So in order then to make use of this data, everyone should be aware from the beginning of this possible critical point, and maybe just select part of the data which are not affected by this effect. On the same day, again, looking at the diurnal course, what we can see is the photosynthetically active radiation, which is calculated as an integral in between 400 and 700 nanometer. Here you can see the typical bell collected during a clear sky day. In red, you can see the data which are later on filtered by the quality flag criteria, which were collected under changing illumination condition. And then some of the indices which can be calculated, like the MTCI, which gives us an indication of the chlorophyll concentration, or the NDVI, which is rather well known and mostly is about greenness and biomass as well. And finally, the fluorescence, in this case calculated at far red, so at 760 nanometer. And also here you can see that the vegetation indices has a less variation during the day, and most likely this variation is not indicating a change in biomass or in greenness, but is an artifact due to this BRDF factor. So this can also be corrected, but it's critical, but it's something that everyone should know before making use of the data. And I was also reporting, this is not the daily variation, but the full time series. In this case, we have only partial data for the last year, because still the data were not downloaded directly. They are sent remotely with a data transfer, but sometimes the network connection is not sufficient to transmit all the data. But you can see that this is the evolution of the 3 years in Spitsbergen. And if we look, for example, to NDVI or MTCI, we can see we were kind of astonished to see that the second year with a so higher NDVI. And so discussing this with Hans, one possible explication could be, or the MTCI as well, that the mean air temperature in the second year in 2020 was way higher than normal compared to the previous one. So it could be, this is still an open question that and the preliminary results, but that could indicate that a warmer temperature had brought to a better evolution or development of the vegetation, and so an increase of the chlorophyll content and the biomass as well. And yeah, I think with this one This was the last one. So I thank for your time, and if you have any question, please feel free to ask.